Right, lecture 6 on enzymatic browning. Click to go forward. Yeah, okay, that's what we're looking at, mostly about polyphenol oxidase. Okay, so enzymatic browning, that's compared to non-enzymatic browning, that this is a Maillard reactions. When an apple is sliced or otherwise damaged, it quickly starts to go brown. This is due to the action of the enzyme polyphenol oxidase. This is a consequence of the plant's defense against predation. It's annoying in a domestic situation because our apples go off, but it's a major cause of losses of fruit in transport and storage. Data is a bit hard to come by, but it may be up to 30% of fruit is lost this way, with significant economic losses. As we'll see, there are ways to mitigate the losses. There's a little video there which gives a sort of general review of what enzymatic browning is. Worth having a look at. Okay, so the basic chemistry involves reactions of phenol with oxygen. This process being mediated, that is to say catalyzed, by the enzyme polyphenol oxidase. As mentioned, it's a natural part of what happens when fruit's damaged. It evolved for the plant's own reasons, just has impacts on us. Okay, so this is a picture of a chloroplast. Thialkaloids are collections of disc-shaped, the name literally means sac-like, structures inside chloroplasts. They're involved in photosynthesis. That's obviously outside the scope of this discussion. Our main interest is that their membranes contain polyphenol oxidase in an inactive form. When the cell is damaged, PPO is released and activated. As mentioned, it acts against pests, but also promotes browning reactions in the plant's phenols by mechanisms we'll have a look at in a second. The potato aphid is a significant pest. The aphid may transmit over to 50 plant viruses, including potato leaf roll virus. It may be responsible for annual losses up to 20 million tonnes of crops. There's a couple of words here which you may not come across. Trichromes are the small hair-like structures on leaves. So when, for example, a potato aphid eats a potato leaf trichrome, it injects polyphenol oxidase, which reacts with phenols in the aphid's mouth and mouth parts, producing a gummy residue which stops the aphid from eating. So, as I said before, PPOs evolve for the plant's own reasons, just happen to be an economic issue for us. Okay, so the enzyme polyphenol oxidase is a tetramer, so it's a quaternary structure. In general terms of protein structure in general. It contains 4 copper atoms per molecule and has 2 binding sites for aromatic compounds and oxygen. Here's a cartoon showing and these pictures are called cartoons. A picture of a cartoon of PBO showing the location of copper atoms and the binding sites. You don't, of course, need to remember this, but you should be able to discuss the PBO structure in general in terms of exam questions. Okay, so when an apple is sliced or otherwise damaged, PBO is released and comes into contact with oxygen. This allows the reaction to start, and the apple in this case starts to go brown. Okay, so what's happening here? It involves reactions with phenols. A phenol is an organic compound which is an aromatic ring system. That's one of these things here. To which is attached more than one OH or phenol groups. When only one phenol group is attached, this is called a monophenol. Note that R, as usual, designates just any other group, and it could be quite a large molecule which has been designated by R here. As you might expect, a diphenol contains 2 phenol groups. The rules of chemical nomenclature mean that we number carbons to which the first phenol is attached as 1 over here. And then we use the lowest possible number for additional groups, so the second phenol is number 2, hence this is a 2-diphenol. So here's a reaction. The first stage reaction involves the formation of a diphenol. This is an oxidation reaction. Bring that up there. Since another oxygen atom is added to the phenol ring, hence the enzyme is called an oxidase. The second reaction produces a molecule called a quinone. This is again an oxidation, which can also be defined as the loss of hydrogen from a molecule. In this case, the 2 OH groups are oxidized to produce 2 C double bond O or carbonyl groups. After this, the products react further to produce dark complex polymers called melanoids, but they're outside the scope of this lecture. There's a lot of very complex chemistry involved in this. So here's an exercise for you to try. You go back a slide and have a look at what happened in the example reaction we saw there. Pause the video if you're watching the video. Predict the products of this reaction. Think about the parts of the molecule that would take part in the reaction, and don't worry about those parts that don't. Okay, so I'll assume we pause the video here. Okay, we're back. Again, we have a two-step oxidation. The first is to add a second phenol group, and the second to convert the two phenol groups into carbonyl groups. And as mentioned, these parts of the molecule don't take part in the reaction at all. They just happen to be the characteristics of this particular molecule. Okay, here's another example of a go at. In this case, think carefully about the molecule you are starting with. So again, if you're watching the video, pause the video. I'll take a momentary pause myself here. Okay, so we're back. Let me just go back one slide before I go there. Okay, so just a little bit of discussion about this molecule dopamine. It's common in plants and animals. It's a precursor for neurotransmitters in humans, interestingly enough. Okay, so back to the reaction. The first step has been carried out in that it's already got one OH group. So what we're looking at is the second reoxidation of the two phenol groups to the two carbonyl groups to produce a quinone. Okay. Just as an aside, if we start with either the amino acid tyrosine or dopa, we end up with the same product. Just a mild curiosity there. Okay, we're doing for time. Okay, right, so inhibiting PBOs, which is an area of considerable interest. There are a number of ways of inhibiting the actions of PBO. You can pause the video and have a read through this yourself. They all act to slow down the reaction, so hopefully reducing economic losses. So I'm not going to read through them. You can have a read through them yourself. And here are some examples of how it's done. The one at the top is probably one of the ones we're most familiar with, and we'll have a look at some examples of that in a minute. Sulfide's added to quite a lot of things. It is an allergen, of course. Blanching potatoes is basically when you put the potatoes briefly in hot water, or boiling water, then take them out. You're not actually cooking them, you're just heating the outside. And we'll look at gene silence in a little while. Okay, so guacamole, an avocado-based sauce that goes very quickly brown due to polyphenol oxidase action. The action of chopping and blending the avocado greatly increases the surface area, and hence the exposure to oxygen, greatly accelerating the reaction. There is a good way of stopping this, which some of you may well already be familiar with. One myth, though, leaving in the stone does not inhibit browning. So how can we inhibit browning? So this is Harold McGee, professor at Yale, who conducted an experiment to find out what is really going on. Here's detailed in his book, The Curious Cook, or Kitchen Science and Law. He found a significant exposure to air. Only the area of the guacamole directly in the pit had not undergone oxidation, replacing the avocado pit with a light bulb had the same effect. And we can see in the images here what's happening. So with the pit, it makes no difference. Normal, very similar to with the pit, but acidified with lime, reducing the pH, therefore affecting the activity of the enzyme, does slow the rate of PBO action quite significantly. McGee's probably most well known for his book on food and cooking, which is a great resource for anyone interested in the science of ingredients in cooking. Well worth getting hold of a copy, particularly when you get a hold of a second-hand copy. Okay, inhibiting PBOs using ascorbic acid. Mentioned using citric acid there. In both cases, they're lowering the pH. This is something you're familiar with, sliced fruit. In packaging, oxygen is removed and replaced with nitrogen and carbon dioxide, and that prevents PBO from acting until, of course, you open the package. Most people barely notice, but when the pack is open, the fruit takes much longer to brown than normal fruit, even things like apples. There's a reason for this. It's because in many cases the fruit has been sprayed with lemon juice, which contains ascorbic acid, vitamin C. Now, this acts to inhibit polyphenol oxidase in two distinct ways. First, Ascorbic acid reacts with oxygen itself, producing dehydroascorbic acid. This is said to be oxygen scavenging and reduces the amount of oxygen available for the PBO reaction, so reducing the rate of browning. It also takes part in this reaction. If you have a look at it, it is effectively reversing polyphenol oxidase oxidation. It goes from a quinone to a 2-diphenyl to a phenol. Okay, I'm going to pause there. We'll go to a second part of the video